try to give you the final construction and that's it. Okay. Let U be a universe of size n and B be a positive integer. B be a positive integer. Okay. And what we'll say, let, I think the voice is coming. Okay. Let chi be a collection of, let chi be a collection of functions from U to B, right. So what is this? These will be a family of functions. So chi is going to be functions f1, f2, some f r, where each fi it's a function from universe U to B, which is basically 1 to B. Okay, okay. Collection of functions from U to B. The collection chi is said to be pairwise independent if for every I comma j in 1 to B and every u comma v in U such that U is not equal to V, we have that probability f in chi I and 1 over B square. Right. So this is the definition of, this will be the definition of pairwise independent family. Okay. So when you pick a random function, your chi is nothing but space of all functions from universe to B, right. But now I am defining with respect to a particular family. Okay. Chi, the collection chi, and when we were taking a random function, then chi is all functions from U to B from where you are sampling. It's called pairwise independent if for every I comma j in B and every u comma v in U such that U not equal to V, we have that probability f you are selecting from chi, f of u equal to I and f of v equal to j is 1 over B square. So when I look at these two guys, they are just like independent, pairwise independent. Okay. Okay. So what does this also implies? This also implies something interesting, is that any pairwise independence family of functions from U to B with cardinality of U greater than or equal to 2 satisfies that for every I in B okay, u in u we have that probability, right, again f is in chi, right, because you have to define your taking probability over what, right, f of u is equal to I is equal to 1 by b. If this is a definition, it implies this. Do you see? Just sum over everything. That's it. So like if u takes y, just fix another v, it takes something, 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 and if you sum over that, it's b times 1 over b squared. So it is 1. Like this is it, right? Okay. I have no look. What? Tell me. Yeah. No, we will do sum over all element of what is that called? B, not the universe, because u is fixed. This is really a simple exercise from here. So please, if you do not know this, it's a very good exercise. You will understand something about probability. Please treat that as an exercise. Okay, really exercise. I mean, try to do them. Otherwise, okay. So what we will use is the following proposition. Okay, a well-known proposition. I think it was proved by. Let me see if I have. Elon, Babai, and Itai, 86. Okay. So what did they tell? What did they give us? They gave us something very nice. So there is a polynomial time algorithm okay. So what if there is a polynomial time algorithm that given a universe u, given a universe u an integer b constructs a pairwise independent family chi of functions from u to b and of size how much from it. There is a polynomial time algorithm that given a universe u and integer b constructs a pairwise independent family chi of function from. Okay. The size of chi is what n square, and it does not depend on b. B could be anything. Of course, b has to be less than. Okay, so that many functions. Okay, so this is what the proposition says, right? So I'll give you functions of world this much. Okay. Okay. So as I told you before, the way to use this is first think of chi. This is what I spent my last whole lecture. Is that first think of chi as all functions from u to b, and if you are able to prove some properties about these objects with just pairwise independence, then if you are looking for functions which satisfy those properties, then you should be able to find those properties among these functions, right? That's all. So this is how you should use them. Okay. So what did we show last time? That using pairwise independence, we can come up with, just by pairwise independence, we said that, if you recall correctly, that we said that, well, we can come up with f from u to b in such a way that in each bucket things go roughly the same, right? Like almost equal to its mean and everything, right? So now I'm not going to tell you that, but now I'm going to give you construction, and in the proof that why this construction works, those properties will be used. Okay. So what is the construction? So what am I trying to construct? Okay. So I'm trying to construct, if you recall recall correctly, so we are interested in NPQ set inclusion families, right? And what is this NPQ set inclusion family? It's basically a family F of functions x1 to x r star, okay? Each has size equal to q, right? Okay, and for every y element of universe, choose p, right? P, there exists some xj such that xj is a subset of this, right? So we would like to cover all. This is what we are looking for, and of particular size. So this is our objective. Okay, this is what we want to construct, right? So now next, what I'm going to do, I'm going to define. I'm going to use these functions for my division purposes, right? And I told you that there exists a construction of this, right? There exists a construction. Another fact which we already proved, or lemma, there exists, if you recall correctly, last time proved, okay, there is an algorithm, okay, that given n, p and q outputs an n, p, q set inclusion family C of size at most kappa, I'll tell you what it was, times n to the power big O of 1, right, in time 3 power n. Okay. Okay, what is kappa n power p? We'll fix this here. It is divided by p just go, right? This is what it is. Okay, just as a simple form. Okay, so this is what it is, right? So now I will combine these two to get our desired things. Okay, so now the construction. Of course not. I mean, what did you learn in the data structure course then? Why? This is the part of, this is what I asked you two people to learn in data structure course. I'm sure he must have done how to do k pairwise independence and all this kind of thing, right? So why should I give proof to this? That's not my purpose. Okay. Okay. Set beta equal to q by p. Okay. And set beta equal to q by p. Select a number b equal to order log n. Okay, these are like buckets. Order log n of buckets. Okay, and apply proposition. Let's call it. proposition A. Fine. Apply proposition A to construct a pairwise independent family chi of functions from U to B, right. So, I set beta equal to log n and I apply this proposition. So, it will give me some chi, some set of functions, and how many such functions are there? Order n square such functions are there. Okay. 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 Now, for each function f in chi, okay, for each function f in chi, an integer I in B and an integer I in B, I am going to define just the way we define. So, we are just trying to mimic whatever we did last time. An integer I in B be set UIIF, right, those elements which are mapped to an integer I by f, that is it. So, basically U in U, okay, and f of U is equal to I. So, basically you can think of this is nothing but set f inverse of I, right. This is basically what it is, right, yeah, f inverse of I. And I am going to use the symbol n of I to denote the cardinality of this set, okay. We call a function good, okay, and you will see this is where good. We call a function good if for every I in B, now it should remind you what I tried to define good last time. If for every I in B, right, we have that, what you want to say, that this number is not too much away from the mean, which is n over B, right, like the number of elements of universe which are mapped to each index is not too much more than n over log n, okay. We have that is NIF, which is a number, okay, minus n over B, which is its mean, right, is at most root n times B, okay. Then we call such a function good, okay. And if you look at the last time's computation, what we know that at least one of the function is going to be good for our purposes in this particular chi. Of course, we know that if I take all functions, there are functions which are good, but among this small collection of chi also I will find such a function, because as Rohani was saying, just take first n by log n, map it to 1, next map it to 2, and so on and so forth. But that function is also a function from U to B, but that may not be part of my chi, right. All I can guarantee from chi that I have such a function, okay. Okay, fine. Okay. Not yet, nothing, you don't know, there is no S, right. S is a part of analysis, S never comes. S cannot come in the construction, right, because you have to work, I mean, like no S nothing, like it should work for every Y, right. So, it is an independent of Y, right. So, my construction has to be independent of I. Look, whether a function is good or not, looking at function I can check. Whether a function is good or not, I'm looking at function, I can check, right? Because I know my universe, I can just check whether this number is satisfied or not. So what do you like to do it? Now, if you go back in the proof, we tried, for every S of size P, there will be someone who will also be dividing it equally, right? Now, what I would like to do, that for the covering family, I also want to cover it fractionally in each part. I do not want to cover, what I mean by this, so suppose, think of this way, that this is my line, this is my buckets, right? Now, for every S, there is a bucket where both F and S goes properly, okay? There are many ways to cover this S, like to find this particular Xj, whatever I could do, I could cover completely here, some here, and so that its size becomes equal to Q. That's okay, right? I mean, nothing. But I do not want to do it. I want to also cover them fractionally here so that my bounds holds, right? So what I mean by this, so whatever this is, I want to cover what fraction of this? Like, okay, fine. You are this fraction, I will cover 1 by bth fraction of y also here, right? So I'll cover you that much here, I'll cover you that much here, I'll cover you that much here, and I'll cover you that much here. And I'll take these unions to find this desired Xj, right? So I could have taken, look, this construction, I could have set whatever it goes, I could set P equal to Q for all that you care in this guy and then cover everybody. But that computation doesn't work. So you cover it fractionally in the sense that, okay, fine, I need a P size object to cover, sorry, I need a Q size object to cover this P size object, right? So let me cover Q by Pth fraction of that here, right? Or no. So what I'm saying, so what I will cover is P by B here, fraction, another P by B fraction here, another P by B fraction here, another P by fraction, so that in total they are equal to P roughly. That's the whole idea. Okay. So I will call this lemma second construction appropriately. Okay. Do you get the idea? Yes, but what I want to say, look, all I'm trying to do is, look, that S has been divided into, that S is the yellow part. Let's call that, I call it Y, right? Let's call this Y has been divided into Y2, Y3, dot, 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 YB, right? Now, I can cover completely Y1, and that is also part of Y, right? And my objective is, given this Y, I want to construct Xj. But I do not want to construct Xj which is completely contained, which is equal to Y1, for example. I also want to construct Xj which covers little elements everywhere.
Okay, so when we say little element, we are basically dividing this Q. Each element is roughly Q by P.
Each element is rough.
Each partition of this Xj. So sorry.
Each element of this partition is roughly like P by B everywhere.
That is for Y.
That is for Y, right? Xj, Q by B. Yes. So I'll cover this here, Q by B. I'll cover here, Q by B. I'll cover here, Q by B. I'll cover here, Q by B. Okay. This is what my goal is. I might over cover, but I will cover them, right? So I will apply this lemma with, try to apply this lemma with P by B and Q by B here, P by B and Q by B here, P by B, Q by B here, P by B and Q by B. Suppose for now that P, Q all divides B properly, right? Then actually I will do some ceiling and floor to take care of everything, but the overall idea is that everyone has, I know that first of all, my big universe has been divided uniformly. For every s or every y, there is some function which is not only divides u uniformly, but it also divides that particular y properly. Okay, and then I'm saying, look, I'm not interested in covering you completely here. You will be covered together when I take. So, for example, to here, I will cover some xj1, xj2, xj3, dot 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 xjb, right? So, the covering object for y will be union of xji. This is what it will be part of y. This is what I'll try to prove, right? So, but what I do, I even for that also, I say, look, there are p elements I need to cover, right? I will take, sorry, q elements I need to cover you. So, I will cover q by b of here, q by b of here, q by b of here, q by b of here. So, that's the whole idea, okay? Now, all I'm going to do is to make that symbolically correct. Okay, so this is an idea. So, this is what we are trying to implement. Okay, this is exactly what we are trying to implement as an idea. So, what are we going to do? For every good function f in chi, right? Those which are not good functions, just throw them out. I mean, they are useless for our purposes, because I know for every set y there is f which will be good and everything. So, that's perfectly fine. Okay. For every good function f in chi, I in b, okay, and every integer, okay, every integer, okay, s less than equal to NIF, every integer s less than equal to NIF. I know how much NIF is. We construct and NIF s, okay, beta s, I have set beta in the beginning, beta s, set inclusion family, C I S F using lemma b, using lemma b. Okay. So, what I do, I construct this object, right. For every s less than equal to NIF, I construct. So, basically think of this s as being the guess of the size of your intersection of your y with the first part. This is what you should think of them. Now, what is beta s? Is basically the appropriate fraction of that which I would like to cover, because what will happen if you think of this way, what it will cover? Suppose I have a s size object and I have covered beta s here, right? So, what is beta? Is q by p, right? So, beta is like q by p into f, right? Beta, so how, so this is times b, right?
All the size. So fix an integer y.
Yeah, so we'll have to sum over this, then it will become exactly what it is. Fine. Yeah, so that's the whole idea. Okay, you will see in a minute. Okay, more detailed what it is trying to do. So, for example, say S1, S2, S3, F beta, and this is like some number t, whose sum is this, like t is this summation ti, summation si, okay, because I already use s, so I do not want to use this. So basically what it is covering. Now when I apply this beta s, it will be q power p si, right? In the ith box you will be cover q by p times si. So I mean all this, if you forget all this ceiling and floor, then this is how much you will cover, right? So if you take out q by p out, what you will cover is like t. Hmm? Yeah, so suppose this t is p, so this is p. So what did we cover?
We got a set of size q, which will be our x.
Which is our, because pp will get cancelled, right? So if p gets divided into s1 to s beta, right? So you are covered in each part q by p times si. So if you sum them over q by p times si, this is not what will happen because there is ceiling here. Okay, so things you might be over covering it, so you have to subtract it. Why? Because if you are covering with this much, you might be covering one extra, right? Maybe in some it divides properly, so you are not covering. So you have to be careful. You might over cover it, but then you can under cover it by deleting. Look, because it's a ceiling, right? You might cover one extra element each in each bag, each box, right? But that's okay, right? We have only over covered it. We can forget about those things later. Okay, but roughly if they were equally divided, then you will cover summation q by q divided by p times si, where each si is going to be equal to p. So q by p will get pp will get cancelled, and you will cover q elements. Okay, so that is what the s will play a role. Okay. Okay. So now what we do, so our construction is following. Okay. Okay. We now describe the construction of C. Okay. Each set, I don't know why I write y here, but okay. Okay, I'm going to, just for familiarity sake, just for the familiarity sake, I'm just going to. Okay. Okay, just for the familiarity sake. Okay, each set, so that when you read it, I mean you is described by, each set y in C is described by, okay, some few things. Okay, a good function f in chi, that's one thing which I will use. Second, a sequence p1, p2, p beta, no, pb of integers, okay, such that pi minus p by b is root n times b. Okay. Third, a sequence y1, y2, yb of sets in where? Sets with yi being element of what? Ci, pi. I have constructed here, right? A sequence y1, y2, yb of sets with this, right? I will tell you what is this tuple is defined by. I will tell you a function f, sequence of numbers, and some sets y1 to yb, where each yi belongs to IPI. I have constructed IPA. And finally, a set D, subset of U of size at most B. This is what I will tell you. Okay. So this is how you this is my construction. So I will, to construct this, I will, this is my construction. What I will do, so it's basically a tuple where first is a function f, which is good, and then some sequence of integers p1 to pb, where this property is satisfied. Third, some sets y1 to yb belonging to this, and a set D, a subset of E of size at most b. Okay. But I have not told you how I am going to define Y. The set Y is defined by the tuple. Okay, what is defined by the tuple? F P1 to PB, Y1 to YB, and a set D. This is it. The set Y defined by the tuple this. What is this tuple? What do you think it should be? What this Y should be? Given by this tuple. Look, what are these basically? These are the people which are contained inside the set you hope for. And this is trying to take care of the extras which you would have covered. So this is basically union I equal to 1 to B yi minus D. That's it. This is the end of construction. This concludes the construction. That's it. These are my sets. I might have constructed many more sets than required, but this will satisfy all the property I want. And it will have the desired size which we are hoping for. Look, I have just reverse engineered everything from what I tried to prove last time. Right. What is this function? Sequence. Look, I know what this sequence tells me. This basically tells me how many elements of your x which is in your head has gone to each part. So that is quantified by P1 to P2 to PB. Now I have already computed for all s less than equal to NIF. So in particular I have computed Pi also, because Pi has to be less than equal to NIF, such that what is the property? Pi minus P by B, because P is in your hand, it's not too much. I mean, it's not too far away from this, and we know such good functions exist. So this is where I have used a good function, and like, so I have all functions, right? I have, like, in my tuple, I will go over all functions, I will go over all partition, I will go over all yi, and I will go over all d's, right? I will tell you how many of those are. Now, if you have a particular set x in your head, right, then there exists an f which is going to do good with respect to that x, right? So now with respect to that x, I have guessed these integers P1 to Pb, right? So, and they are satisfying this property. Now with respect to that, I have applied y1 to yb, and this construction tells me that for those guys, I know yi is going to contain inside this for some value of y. So fix for all those guys. There will be some place where I have fixed, because I am going over all sets. Look, y1 to yb is all sets in the first coordinate times all the sets in the second coordinate times all the second, like, so it's like, it's a tuple. How many, we'll see how many we created, and D is of size at most B. So those places where you have covered that extra, maybe, I don't know, but you will cover at most log n extra, because there are only log n bucket. So B buckets, right? So I don't know, maybe in some you have covered equally, so I really don't know. So I cannot guess this. So that is why I'm covering D of size at most B, right? So If you have not taken anything extra, then when D is empty set, you would have got that set, right? That's the whole idea. All of you look very confused, Rani. Why are you confused? No? Okay. Now, there are several questions. Okay. So, this is my construction, end of this. I'm going to, there are two things to consider. Why, first of all, why it's correct, what's the running time, and what's the size. Okay. So, first let's analyze the running time of this construction. Okay. Okay. And then we will worry about the size of this family. Yes?
We don't have anything on D except its size, right?
No, nothing.
Why not just take the proper set of this union of size? Why do we need this?
I don't care. That's the reason. It's like I just don't care, right? I mean, yes, you could do that, but that doesn't give you anything extra. It depends on what my goal is, right? If in my goal it does not, then why should I complicate life for everybody else? Right? I have a goal to achieve, and this itself achieves the goal, so I just put it like more down. Look, I could have. Why am I constructing all S less than equal to NIF? Think about this, right? I mean, this also could be overstatement, but I don't care. In the grand scheme of things, they don't like. I have already spent a lot of time here because I construct for all NIF, right? But those do not care. I like those do not like. I have already computed all of them and kept it, and then I'm just going to use them. I'm not trying to be what you call superly efficient, because even in the worst case, I'm going to be just exactly like that. So I do not care. I mean, it's for in ease of presentation. Let's put it this way. I overachieve this. I have many more sets probably by some factor, by sub-exponentially factor maybe more sets than probably I need. But that's okay. It's only sub-exponential, so that's perfectly fine. Okay, so running time. Running time. So first what we construct this chi. That construction takes polynomial time, right? Chi takes poly time. That's one thing. Okay. For each good f in chi, right? For each good f in chi, I in B, right? Right? How much will be Ni of f? Is less than equal to at most, right? Some root n by b. I'm talking at most, right? Because it could be this, it could be that. But what is b? Roughly like log n, right? You can put some log n plus 1 if you wish to. But this is exactly equal to order n divided by n log n. Root n log n cannot exceed n divided by log n. So this is big of n log n. There are order n square choices of f. So maybe all of them are good for all that I care. I don't know. Okay, so what should I rub now? Okay, what should I rub? Maybe I should leave this for some time. I'm going to rub this. I hope you have not it up. Okay. and how much time constructing CFIS takes. Rohani ji, how much time does the construction takes? Yes, but what is NFI? So how much time it takes? 2 power little of n. N by log n is 2 power little of n. I mean, okay. So takes 3 to the power big O of n log n, which is 2 to the power n. Okay, irrespective of what my S was, right? But how many S are you going to consider? Polynomially many, right? 1 to NIF, 1 to NIF, 1 to NIF, 1 to NIF, right? I mean, really, right? Summation NIF, which is, so I can construct for all I and for all S less than equal to NIF, I can actually construct them into 2 power big O of n, because it is going to be 2 power little of n times some n, which is again this. Okay, so I can construct all this in sub-exponential time. That is why I do not care, because I can construct all of these things in sub-exponential time. Then I do not care. If I'm hoping for an exponential algorithm of 1 point blah blah to the power n, I do not care about the lower order terms. So now, so thus overall running time is, look, so I have constructed up until here everything, okay. Thus thus overrunning time is upper bounded by what? 2 power little of n plus and how can you output C? I can output C by spending polynomial time for each y in C.
What you have written, there are order n square this running time.
Where?
There are order n square
Choices of f.
choices.
Okay. Look, I need to output y. So to need to output y, I can output this tuple, and I can output each of this tuple in polynomial delay, right? I fix f, I fix this, I have constructed this, I go over, you just need to keep some indexing, so I can output each of this tuple and hence each of this y in polynomial time, right? So the overall running time of this algorithm is, once I have done some pre-processing in 2 power little of n time by getting my f's ready, by getting my CISF ready, all I need now to construct your family C is I'm going to take time proportional to C times this much, okay, or in other words, number of tuples. This is what I'm going to take to construction. Now what I'm going to do is try to bound you the size of the tuples, how much tuples we are going to consider, right? Because once we are done with that, then that will give us a desired upper bound on the size. Okay. 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 So now let's look at the tuples. How many choices of f do we have? So let's write down for n square. It doesn't matter. How many choices of pi I have? NIF at most n. So NB, n to the power b. Okay, fine. Okay, how many choices of D do I have? At most n to the power log n, because or that is also I can say some n to the power big of b. So all it depends on now the cardinalities of, right? Like what are we computing? So for each sequence we are going to, which satisfy this property, we are going to construct these guys, because we are only going to use these guys, right? For each particular choices of P1 to Pb, we are just going to use this thing, right? So what it will be, okay? Choices of y1, yb is upper bounded by, because that is what we have not taken care of, bounded by question, this is a question mark, we want to bound the choices of y1 to yb, because once we are done with that, and with this, now we need to be clever, because we cannot be more than n choose q divided by p choose q. So now we need to be, because that is what we are hoping to get, right? That our construction has size n choose q divided by n, yeah, n choose q divided by p choose q into some sub exponential factor that I'm willing to let go, right? Is upper bounded by what? Product I less than equal to b kappa. Remember, I wrote some symbol. For kappa, I wrote a symbol here. What was that? NPQ was just whatever the number I was trying to tell, so that we do not have to write. Pi, beta pi, times n to the power big of 1, right? This is the construction comes from here. Here. This is what I'm going to apply, right? NIF pi beta pi, right? Product over all I less than equal to b. Is this right? Because each choice is of, this is a choice for y1, choice for y2, choice. I'm just multiplying, and I will multiply this finally over here, and then I will be done, right? Up until now, if you notice, all these are sub exponential terms, so we can just forget it.
So this product over this I less than equal to b, this is the total number of choices of y1, y2, yb, that one, right?
Yes.
Okay.
Yeah, this one, right? Is upper bounded by. Okay. Now, let's forget this n to the power big 1, because it is at most some log n, so that is taken care of 2 to the power little of n. So this is 2 to the power little of n, not big O of n, little of n times product I less than equal to b, okay, NIF pi, okay, no. What is this? Okay, beta pi divided by pi choose beta pi. Agreed? This is what our construction will give us. This is just the, this is the value of kappa in this term. Right? Okay, fine. Now I'm trying to bound the top term separately and the bound the bottom up, lower bound this, upper bound this and lower bound this. Okay, product wise, because if it is product, I can take product on the top, product on the bottom. Okay, so let's see what we can say. Okay, let's see if you people agree. Hopefully, and if you don't agree, please do it. I'm very bad with all this. NIF beta pi, okay, is less than equal to, okay, pi I less than equal to b n choose b. I'm only bounding the top guy, okay, p by b times n to the power big of root n log n. I want to say this. Right? Do you see why this is correct? Look, NIF is upper bounded by what? Roughly n by b plus some c root n. And what is p by b bounded by? P by b is also bounded by, yeah, root n times b. Right? Pi, like basically this plus some little terms, right? And I'm claiming that that little term is upper bounded by all those things. Okay. If you do some Stirling approximation, all this is okay. This one is trivial. Next one is not. Next one is easy, but if you know this, it's easy. This is less than equal to n choose p to the power little of n. You know why? So you see what happens. So think of this way, that you are picking up p by b elements from a universe of size n by b, right? This is what is happening. And imagine yourself picking a set of size b times this from a b times this universe. Like, so think of this way, that you have a fragmented world. From each you are picking some things, right? But the same set, so look, this is why it is, like the intuitive explanation why this is correct, why this is fine, is that, what should I rub? We need to rub anyway in some things, right? I hope you have written this, so that when, if you need to go back, you can go back. See. Okay. So what happens, that you have a universe, okay? You have a universe, okay? You put a sticks, right? And you are trying to pick a set of size, some fixed size, say b, or say not b, let's say some size x, okay? So how do you pick this? You say, okay, look, I'm going to pick x1 from here, x1, like some b times. So suppose I'm going to pick x1 by b from here, x1 by b from here, x1 by b from here, and x1 by b from here. This is what it is. And now I tell you, so all this is going to give me a set of size b, set of size x. Why am I writing x1? Sorry. Right? This is going to give me a set. And now I tell you, from the whole universe, just pick a set of size x. Now you're also allowed to pick a set which can contain not x by b, some little here and some more here. So you can only create more sets. You will not create less sets. So this is an intuitive explanation of the last transition, right? So basically this is upper bounded by y, because you are looking, so you are choosing an p by b sets of the universe of size n by b, right, in each. This total thing is upper bounded by choosing b times p by b size object from b times n choose b size object. So this is exactly where it comes, and the rest is taken care of this. Look, they are divided in a way that gives you this number. It's all pre-computed, right? If my math had not have been working, where? No, you have taken care of product. This is exactly what it is, right? Like this is why product is like, okay, think of this way, that you have a, you want to find a, look at all the family, all sets of size x from here, all sets of size x from the whole universe, right? Of course, that family, now look at the sets of size x which you can create by this process. Clearly they are sets of size x, so they are contained inside my family. But your family also contains some sets which this process cannot make, and that is why they are upper bounded. Everything which you can create is a set of size x, but I can create many other sets of size x which is of not this form. For example, I can take one element from here, huge number of elements from here, right? Those sets are not considered here, right? This is only considering those sets which picks certain amount of objects from each part, and that's it. This is exactly what has happened from here to here. Question? Is this intuitive explanation not correct? Because this is all that you will find there. I will not write more than that. This is correct, and there's nothing more to this. So this is exactly how you get this. This is because of some extra term, you apply some Stirling. This is like over a statement. This is like really over. It's like, think of this when you're writing down this terms in this. There's some small terms, you put them n. This is what it is. Last terms. Okay, fine. So I should give you now a lower bound also, so that I can give an upper bound. Okay. So this is an intuitive explanation. Okay. So if you read the paper, you will see this explanation. By the way, I am not writing this explanation. Doesn't mean the person who is making notes does not have the right explanation. That's something which you have to work out. This is the whole purpose. I mean, I can give you explanation, but why should I give you explanation? At least for this, I know explanation. I gave you hint. So whoever is making this notes should write explanation. That's the whole purpose, to make you people work out details. Okay, fine. Okay, so now we have product I less than equal to b. Okay. Yes. So there is a, I mean, if you read it, there are like some very well-known inequalities known about this binomial coefficient. So you just use some of those guys. Okay. So what is this? Pi. What is this? What is down?
Beta pi.
Beta pi. Right? You can show again using. So if you look at the paper, there is an inequality which we use. It's written there. Okay. It's not. I mean, you look very shocked. Okay. So look, you can upper bound this term by this. You can lower bound this term by dividing by the same terms. Beta times p by b, choose root n log n minus this is, at least I wrote this I wrote last day. So that expression what I wrote that day, you can lower bound and upper bound both terms. Why people are calling me? Some बेच रहा है कुछ. Okay. This is equal to beta minus beta 1 minus beta, beta minus 1 b divided by b times n to the power minus 1 to the power b, and I have made even more something. These are computation, Rohani ji. If you ask me for this and that, it will be difficult. Again, but if you recall this term, what was it? This was roughly equal to P choose B, P choose Q. And this is how you get your bound. This is how you get your bound. Do you remember this term? N choose alpha, N is blah blah blah. It is exactly that. That's basically what I've used. Nothing more. I wrote this that day, right? N to the power P by B. Okay. So this is how you. So you lower bound this, you upper bound this. I mean, these are like simple computation which you people are much more better than me. So let's not spend time. That's not the point of energy. This is how you construct things. Okay. And what you constructed has the desired side. That's all that it matters, right? You just multiply them. This is an expression, and you can prove that this expression is good enough for you. And how do you? You upper bound the top one, you lower bound the second term, and that's it. That is a message to take, not how I do computation. That's worthless. That's not the point. I mean, you people should be, at this point of time, all of us should be apt to do these kind of computations ourselves. Okay, fine. But now, why is this correct? Right? Why is this correct? Well, so now let's consider a S subset of U, cardinality of S equal to P. Right? Let's fix this. What we know by our last time computation, we know there exists F such that, what was the property of this? There exists F in chi such that UIF minus n by b is less than equal to root n times b. Remember, this is your, there exists F in chi, so that UIF minus n by b is less than, forget computation, Rohani.
What is the size? The size is also sub-exponential.
This term into sub-exponential, yes. Sub-exponential, we don't care. I mean, you like, imagine yourself that you're fighting for 1.98 to the power n algorithm, right? I can write 1.981 and get rid of any sub-exponential term, because for large n of n, this term will dominate any sub-exponential term, right? So why to kill yourselves? You give yourself leeway, right? In the settings which I'm going to use, I can increase at 100th place decimal 1, and that to the power n is upper bounds anything. So what I mean by this, suppose you have suppose you have alpha to the power n times to the power little of n. This is less than equal to, for large n of n, alpha point to the power n. All these are zeros. How much ever zeros you want. Right? So that is why you do not care. So in the setting which you are, like if you're looking for 1.356 to the power n algorithm, it's fine to have 1.33666000001 to the power n algorithm, because this is upper bounded by this for some n 10 to the power 10. It's okay, right? So you do not care. So this is why these are the freedom which you provide to make things, because if you do not give that freedom to yourself, rest assured, it's like you may not be able to construct them. Okay. And what we know, UIF intersection S minus what? P by B is also bounded by root n times b. We know this. There exists some f which has these two properties. There exists f in chi with these two property. Okay. Okay. So the construction of our family will be chi n p q 2 to the power little of n. It is not polynomial, it is 2 power little of n. Right? So our choice of f implies f is a good function, right? I am only considering those function which is a good functions. So let us only look at that function for which this property holds. Okay? So that also f will occur here, because all I did in the filtering is that, okay, is this f satisfy this good property with respect to ni or not, right? So I know that in my chi this exists, so I would have gone over that particular function f. So let's consider that function f. Let's fix this function. Okay, so this I fixed. Okay, now what I'm going to say, what is Si is going to be ui f intersection Si, okay, and Pi equal to Si. This is also part of this here, because I went through all the tuples, right? If you notice in my construction, I never said anything about Pi. Just read. A sequence P1 to Pb of integers such that Pi minus P by b is less than or equal to root n times b. That's it. Right? And in my computation, look, here I wrote n to the power b for all that you care, right? So in particular, this Pi also occurs, no? So that fix that f, fix this Pi's. It's there. And our choice of f implies that, what is our choice of f implies? Our choice of f implies, because I am only looking at that which also does this job, right, this job, okay. What does it implies is that Pi minus P by b is less than root n by b. Now, because UIF is nothing but this cardinality of UIF intersection S is nothing but Pi. We just fix it now. Okay. Fine. Okay. Now, what do you know? Since Ci, what are we considering? C f I comma Pi is what set inclusion family? Is an NIF Pi beta Pi set inclusion family, right? What does it implies? This implies there exists a set yi in C f I comma Pi such that yi is subset of Si. Agreed? And what is the size of yi? upper ceiling beta times pi. This is what I said, if you recall. Yes, this is what I am constructing, right? Right. So now I'm going over all sets in yi, right? So let's fix those yi's. So for this happens. So let's fix these tuples. This also will be enumerated in particular. Okay. Okay, fine. Okay. Finally, let D be any subset of y, D be any subset of I less than equal to v yi of size how much? Minus q, right? Look, I am looking for a q side subset, right? So let D be any subset of y of this union of size, you sum these guys and you subtract, right? Any subset, that is my D. Okay. What is the upper bound on D? Note that each yi is bounded by number beta times pi plus 1. Do you agree? This is what it is bounded by, because it is just an upper ceiling. So how much it can be? Thus, what is the D bounded by? Thus, yi minus q is upper bounded by p, right? Each term is bounded by some beta pi plus 1, and there are how many terms? At most b terms, right? So this guy, and after that, what is beta pi? What did we set beta equal to? If I recall correctly, we set beta equal to p by q, q by p or something, q by p, right? So if you do this, right, so pi will sum to p and that will get cancelled. So it is p plus 1 log n times. So this minus this is upper bounded by b, right? And I have enumerated all sets D of size at most b. So in particular, I have enumerated this also. Okay. This implies a correct D is also considered. Okay. So what does this implies? This implies that all yi by our construction or considered is subset of Si, okay, and so y is a subset of S, right? Each y was a subset of Si, right? So if you take their union, is also considered because this Si are disjoint union. So y is a subset of S, and that's it. Okay. Right. And this is exactly what we tried to do it using 2 by independence last time. Any question?
We proved that very early that if we have a C bar K FT algorithm for certain kind of extension problems, then we have a 2 minus 1 by C bar and randomized exact algorithm.
Yes.
But now from this, can like you said that alpha n into 2 pi little of n is. So can I say that if I have a C bar K algorithm for an extension problem, I have a 2 minus 1 by C
To the
plus
n plus
0.1
little of n
by
algorithm.
n.
2 minus 1 by c to the power n plus little of n algorithm.
But with what you wrote, can't I say it's 2 minus 1 by c plus 0.1
Yes.
0.00001 power n?
Yes.
So that's not, I mean, that's much
No.
better than
Why?
power n plus little of n.
Of course not. What are you talking, Rohani? Think about it.
I am adding 0.0001.
That's much larger than any sub-exponential term. That is why you can do this, right?
My running time that I'm saying, first of all, is in the base. The base, not the exponent. The base is 2 minus 1 by c. Okay, this is one number integer plus another integer, and that another.
Yes, but why do you say this is better to write than writing little of n? Why this is better than this? All I said to you that the reason why we do not care, because this term is too small compared to the what you is sitting in front of it. Right? But this is the way of writing is much better than writing 2 minus 1 by 7 c 0.00. That is for our reason that okay, it doesn't matter in this world that this is there. But this is much smaller number than that. For example, I could have n to the power polylog n, for example. Right? I could have made this much smaller. Like, look, this 2 power little of n which I'm using is actually not 2 power little of n. Actually, basically, if you do all the computation, it is 2 to the power big O of root n log n, which is much smaller number compared to 2 power n. Like, you need to have that visualization in your head that this is like exponentially worse. Right? Imagine you prove, say for vertex cover, that I have a C power k algorithm, but it cannot have any sub-exponential term, sub-exponential algorithm. So that is a asymptotic difference between sub-exponential and exponential. Right? So in an exponential algorithm, if I add a sub-exponential term, how does it matter? So that is not much better. That is an upper bound. So this is why people prefer to write this way. Even if you look at universal set construction, we actually write to the power little of p plus q. We could write something to the power p plus q, but that's not good. Why do you want to make your result weaker? This is a stronger result. You don't like this little of n term, or you have some mental block with little of n. Imagine you're doing a data structure. So they keep writing n, oh, this space will be n plus little of n. Have you seen? Hasn't Venkatesh taught you that some n plus little of n, right? And little of n is like n divided by log star n. So for all practical purposes, that is equal to n. But asymptotically, that's like, so it's a fight, that is an extra which you get when you're doing this computation, right? What can you get? So like, people will write 3n plus little of n bits, and if you just go into that, it is like n divided by log, I don't know how many logs. It is. Anyway, this is the end of the class for the day, and this is the end of the class for this week. And from next week, Arindam will teach you pattern covering paper, okay, at the same time. Okay, I'm not here for next 2 weeks, but that doesn't mean that I cannot see in the video and find out whether you are there or not there. That is exactly what the purpose was. Okay, because this is his course, so this is his exam. So please butcher him with all questions. If he doesn't answer, don't let him be. This is his exam. And then all of you have 10 marks for his lectures. Send me your 10 marks out of 10, how you. So what is this? Quality of presentation, clarity of content, and third should be what? How he is able to cope up with the questions. So like based on these 3 things, try to, like all of you, just send me a number. Okay. Okay, sir. And we are done for the day.